All right, thanks everybody for coming. So for those of you who are coming in right now, when you have a chance, go to this URL on the slide, and that will take you to the Jupyter Notebook where we'll be doing all the tutorial exercises today. We're not going to need to do anything there just yet. Philipp and I are going to say a few words about what Ray is, how it works, what the motivation is, a bit more how it fits into the machine learning and reinforcement learning ecosystem. And we'll also say more about applications of reinforcement learning, how reinforcement learning works, and what the basic ideas are. So we'll say a few words, but the vast majority of the time will be used for actually going through these Jupyter notebooks that have exercises introducing the core concepts in Ray and reinforcement learning, and working through how to build reinforcement learning applications in Ray and how to synthesize all these concepts. So that's what most of the time will be spent doing. I'm going to come back to this slide, so if you haven't had a chance to go to that URL yet, there will be more opportunities, or you can ask the person that you're sitting next to. So I just want to quickly introduce Devin and Peter and Philipp, and I'm Robert. And we're all here from UC Berkeley. We're grad students at Berkeley working on distributed systems and machine learning and reinforcement learning and sort of all of this space of problems. So Ray is an open source project that we've been working on to basically unify a lot of the different components of the machine learning ecosystem. So right now, the machine learning ecosystem looks something like this. There are many different distributed computing comes up all over the place. You have new workloads like things like AlphaGo or Dota from OpenAI that are very challenging, sort of have demanding systems requirements in terms of performance. You have applications that integrate simulations and robotics and sensing and streaming data and distributed deep learning and all these things. And so it's challenging currently to support all of these with existing distributed systems. So to say a bit about what the existing machine learning ecosystem is, you have a lot of different standard components. We talked about distributed training and reinforcement learning. Model serving is very important. Hyperparameter search is something that you often do. Data processing and streaming, these are examples of things that people do in the machine learning ecosystem today. However, currently, all of these things, all of these components are standalone distributed systems. So you have things like Horovod for distributed training, Spark, MapReduce, Hadoop for data processing, services like Google Vizier for hyperparameter search. And so this is what people are building today. And when you have challenging or sort of innovative workloads like AlphaGo or other things that are cross-cutting and want to combine many of these different components together in the same application. So maybe you want to do a lot of parallel data processing followed by training, followed by serving, all inside of a hyperparameter search. If you want to do that in a single application, then today you are either stitching together these existing systems in a way that can be difficult, or you're building a new system from scratch. And so that's what we see a lot of at different organizations doing research in reinforcement learning and machine learning, or companies that are deploying this stuff in production. A lot of people are building new systems from scratch in order to sort of meet the requirements of their applications. And so one of the goals of Ray, so we're building a distributed system called Ray. One of the goals of Ray is essentially to provide a single distributed system where all these different components of the machine learning ecosystem can be implemented as applications or libraries on top of a single system. And when you can do that, of course, it's convenient to be able to do all of these things, but the real power is from being able to build applications that do multiple of them together. And so there are both convenience gains in terms of writing the application and also performance gains in terms of not having to transfer data in and out of different systems and into another one. So this is some of the goal, part of the goal. And the way we're actually going about implementing this there's sort of different levels of Ray. So here at the highest level, we have these different libraries that make up the ecosystem. So some of them are not yet built. So we've built libraries. We have fairly mature libraries for distributed reinforcement learning, as well as hyperparameter search. And also, we're working on libraries for data processing and distributed training. We'll highlight some of these in the exercises today. And other people are working on libraries for streaming on top of Ray. So all of these things are things that are sort of going to be easy to use libraries on top of the higher level libraries that can be used out of the box. Underneath that, there's the core Ray API, which consists of two main concepts, so tasks and actors. So because all of these applications that we're supporting are very, very diverse, in order to actually support all of these well, you have to have an underlying system that's both very general in terms of the programming API and also very high performance. So the generality comes from having both tasks and actors, and Philipp will say more about that in a minute. We're essentially taking two of the core concepts in programming languages, so functions and classes, and providing a way to translate those into the distributed setting. And Philipp will go over the API in a second. So underneath the core API, there's the backend, which is, we'll talk more about the architecture to illustrate how that works. But it's essentially these two concepts of tasks and actors compiled down to, or they're not actually compiled, but they translate into to essentially a dynamic task graph that the backend reasons about, and that is used for scheduling, thinking about resources, transferring data, handling failures. So that's all done at the backend level. And so these are the different sort of layers in terms of the Ray abstractions. All right, so Philipp is going to talk about the API.
So one of the requirements here was to make the system in such a way that it's very easy to take existing code and parallelize it. So the Ray API is focused on the two common paradigms for programming, which are functions and classes. And what you can do is you can take some existing Python functions, like for example here zeros and dot. And then you can use the @ray.remote decorator to make the function into a remote function. And then on the calling side, so here's how you would call these. You just say function name .remote of the arguments, and then this call would return immediately with a future of the result. And then in the background, the system will schedule the task. And you can pass these futures into other tasks, and the scheduler will automatically figure out the data dependencies and so on and execute it for you. And then at the end, you can call ray.get on futures to get the actual result. And that will block until the computation has been done, and then potentially ship the result to your machine and return. So that's half of the API. So it's very easy. You take existing functions, you put the decorators at the right places, and then you can call them. In the background, Ray will also construct a task lineage that's being used for fault tolerance. So it remembers how these tasks have been stitched together, and then if one of the machine, for example, goes down and you lose the data, then you can Ray could reconstruct it from this lineage. So one thing we found out while we were working on Ray is that we started off with just a task-based system, but that turned out not to be enough. For a lot of the workloads, it actually turns out that you need to support mutable state. And for that, we introduced the actor abstraction. So you can use this to support things like stateful simulators for reinforcement learning, parameter servers, serving systems, and these other things. And how you do it is you take a Python class, you put the @ray.remote keyword on top of it. These keywords, by the way, can also specify resource requirements. So if you have, for example, an actor that does some training and you need GPUs, then you can specify that in the remote keyword, and then the scheduler will take it into account. So once the class has been made into a remote class, you can then create an instance of it by just saying class name.remote, and the scheduler will find a place in the cluster where there's still capacity, and then create the actor on that node. And then you can just call functions with object.functionName.remote, and you will again get a future of the result, and you can call get on it. these two APIs also play nicely together. So you can actually pass these actors to tasks, and you can also pass results from tasks to actors. So it all blends very nicely together. And you will work on this a lot with the exercises and use these tasks and actors to accomplish various tasks. Yeah, there's a little bit more to the API, but we will see that in the exercises.
If I could just add, so this is the lowest level API, and some of the exercises will work directly with this to do things like model serving and straggler mitigation and things like that. But a lot of the exercises will cover more of the higher level libraries for reinforcement learning. And some of them will combine both together, like using the reinforcement learning libraries to train a policy, and then using actors to serve the policy. And we'll actually have some fun examples with that.
Mm-hmm.
So the question,
So the question was, is the API specific to Python? So the answer is the backend is independent, so that's written in C++ and is language independent. We have mainly focused so far on the Python side of things, because that's where the most gain comes from, and a lot of the users in AI are Python users. However, there's also work currently going on to provide a Java API. So that's actually the first version of that has been released, so you can already try that out. So the goal is going forward to provide more bindings for different languages, but Python is like the main focus for the time being. Yeah.
Is it, I don't know if you mentioned, but is it like lazy evaluation here?
So the question is if it's lazy evaluation. So as soon as you call function.remote, the scheduler will already try to schedule it, and then in the background it will already start running. So it's eager.
So the lowest level API is eager, but you can have higher level libraries, so for data processing, for instance, which can essentially have lazy APIs if they want to, and decide when to submit tasks to the backend. But the backend itself is eager.
Another functionality of this API is you can also start nested tasks. So you can start other tasks within tasks. Many distributed systems don't allow that, but that's one of the things that we explicitly designed for, because that's very useful for these workloads. For example, for reinforcement learning, you maybe have some training that is already parallel, and then on top of that, you're doing some like hyperparameter tuning that is also parallel, and so you can have multiple nested such workloads. Okay, so now let's go a little bit about how the backend looks like and how this is going to map to the actual compute. So here's a toy cluster consisting of 3 nodes, and there's a number of processes on each node. There's a driver. So that's the process that is steering the computation. This could, for example, be a Python script, or in your case, it will be an IPython notebook, which you can log into, and then you can run the tasks and so on. And then these tasks will be scheduled and distributed on workers. So there's a number of worker processes that are going to execute the computation. Also, each node has an object store. So this is a shared memory key value store, basically, which holds all the data. And this is being used for communication between all these processes. So on modern clusters, we typically have nodes with 64 or maybe hundreds of cores. And so we will have lots of workers. And it would be very expensive to replicate the data across these workers. And therefore, what we do is we have one shared memory object store on each machine, which can hold all the data and can just share the data between the processes without copies. And that can lead to huge performance gains in practice. Then there's an object manager, which connects the nodes together. And they are connected to the object store and will ship data as needed. Yeah, so the question was, usually I/O is a bottleneck, and so by exposing this, it could potentially be that I/O will become the bottleneck. So the answer here is that the object store is an in-memory system, and so it doesn't have, and also there's no distributed shared memory. So it's just shared memory in each node. So actually, writing and reading from the object store is at memory speed. So that's sort of the solution. And then the second part of the question was about fault tolerance. So the fault tolerance is actually not handled at the object store level, but rather on the higher array level. So the scheduler, I'll talk about this in a second. There's a part of the system that will keep track of what tasks have been called. It keeps a lineage, and then it can reconstruct things from there. So that's handled on a higher level, the fault tolerance.
Yeah, so some of the maybe more details we should take offline, but the object store using shared memory is actually a super important performance optimization for a lot of machine learning workloads, especially since you have a lot of machine learning workloads have very large numerical data, whether that's neural network weights or images or videos or things like that. And so being able to efficiently share those between workers, processes on the same machine without having to do expensive serialization and things like that it makes a big difference.
Mm-hmm. Okay, then there's also the scheduler. So each of the nodes has a separate scheduler. So tasks are going to be submitted by driver or workers to the local scheduler, and then the local scheduler can determine whether if all the dependencies are on the local node, it can just schedule them on the local node and immediately run them. Or if that's not the case, then it can contact other nodes, bring the dependencies in, or scale or submit dependencies to other nodes. And so this makes the system much more scalable. So with this architecture, to have one scheduler per node, we are actually able to process millions of tasks per second. And then the last important architectural design of Array is this global control store. So this is a sharded database which holds all the lineage information and also information about where objects live. And this makes the whole system design much simpler because it allows us to have all the other components be stateless and therefore simplifies fault tolerance a lot. It also makes it much easier to build tools for debugging and so on. So you can just read out from the global control store what is going on, which tasks are running, and which ones are scheduled, and things like that. And we have a web UI that can visualize a timeline, for example, to see where the bottlenecks are and see what is going on in the system.
Can I take that? Sure. So Ray is an open source project. We're developing it on GitHub. And our goal is to ideally get it to the point where there are a lot of contributors and a very strong community. And this is important because, because we're not just building the back end, but also a lot of the ecosystem and libraries. So a lot of the things that Philipp mentioned, like support for Java, support for streaming, and other higher level libraries, are being developed in conjunction with external collaborators, and so this has been a big sort of boost in terms of development productivity. And so we've had a growing number of contributors. This is something that we had our first release, I guess over a year ago, and since then there's been more and more people at companies starting to use it and develop it. We also have a growing number of industrial use cases, so both in research institutions like Berkeley and OpenAI, as well as organizations of all sizes. And in fact, Ant Financial has been one of the most active developers and has been contributing. They contributed support for Java as well as a lot of other things. So those are. So that's what I want to say about the community. Our goal is to grow it as an open source project and to ideally make it sort of useful for many, many use cases. So now we are going to, so the plan for the exercises today, we're going to come back, we're going to start with, so if you succeeded at going to this, let's see. Okay, so let me zoom all the way back. So if you are, if you haven't gone to this URL, risecamp.tech, please go to that URL and log in. If you're having trouble, can you please raise your hand with that? Okay, so I think everyone has successfully done that. If not, if you run into issues with that, please raise your hand and someone will come help you, or you can ask the person that you're sitting next to.
And in general, if you can't figure out something, then like the bar for raising the hand should be very low, and like we will come and help you.
Can you show the password?
Oh, yeah. So let's see. So there are 3 different directories on that. Well, there are a number of different directories, but there are 3 important ones. So there's exercises, RL exercises, and examples. And there are some dependencies in terms of the order in which you go through the exercises, but for the most part, they can be done independently. So exercises consists of sort of basic exercises about the Ray API, so how to launch parallel tasks, how to create actors, how to use that to do parallel computing. The RL exercises contain a small introduction to reinforcement learning, as well as how to use our reinforcement learning libraries to train some simple examples. And one that I'd like to show you. So this is RL exercise 5, I believe. So it's going to, so you're going to use an RL algorithm called proximal policy optimization. That's PPO. Once you've gone through all of this, there's an actor that you're going to create an actor that serves the policy. And then there'll be a link to actually, this is a policy to play this Pong game. And so this is an untrained policy. So here I'm playing on the right side, and the untrained policy is playing on the left. So of course it's just not doing anything. But you'll find that, well, once you've done the exercise and trained the policy for some number of iterations, then it'll actually start to do well and be a more competitive opponent. Let's see. So that's RL exercise 5. So I especially want you guys to get to that one. And then there's also this examples directory, which consists of 3 slightly more in-depth examples for so for distributed training. There is this sharded parameter server example, which shows how to use actors to essentially set up a number of parameter servers which can communicate with each other and do distributed stochastic gradient descent. Now this is now the term parameter server may be unfamiliar, and that will be explained in more detail in the notebook. In terms of distributed data processing, we have a notebook on speeding up pandas and also one on MapReduce. So Modin, Pandas on Ray, is a project to essentially, if you're familiar with pandas, pandas is essentially the canonical data frame and data processing library in Python. One of the pain points is that it's often very slow. And so this will show, so the goal of this project is to essentially provide the exact same API as pandas, but to make it much faster using Ray. And so essentially you can speed up your pandas workloads just by changing the import statement to this. And this notebook will demonstrate that. And Devin and Peter have been building this framework, and so any questions about this they'll be able to answer. So I wanted to draw your attention to those 3 sets of exercises. Let's see. So the order in which I'd recommend doing them is starting with the basic exercises and doing 1 through 5. That will cover the very basics of tasks and actors. And then switching over to RL exercises. And then at that point, the 3 and 4 can be done in really any order, so based on whatever appears interesting to you. So that can be the examples on data frames or parameter servers or the sort of more involved exercises with the Ray API. Are there any questions at this point?
How different it's from
So the question is, how different is this from Spark? So it's pretty different. It's a lot of the reason for building this library in the first place, or this system in the first place, is that a lot of machine learning applications, and reinforcement learning in particular, are not well supported by existing distributed systems. And part of the reason is the lack of support for stateful computation like actors, the lack of sort of a different focus on performance, whether that's the smallest amount of time for creating like a Spark task and getting the result back is like 50 to 100 milliseconds. And for a lot of these applications, we need sub-milliseconds. So there's just a different performance requirement.
Another one is this nested parallelism. So being able to call tasks within other tasks, that's also very important for these workloads.
Yeah. In order to support all of these kinds of components of the machine learning ecosystem really well, we need a very, very high degree of generality. And I think, so Spark obviously is pretty general, but it's more in the data processing more for data processing workloads. And a lot of machine learning applications are very compute-centric, and you often need to combine these things. So, new results like things with AlphaGo and Dota and such are not done on top of Spark. Okay, so at this point, please go to the exercises or whichever of these exercises look interesting to you, and get started on exercise 1, and sort of go at whatever, go at your own pace, and we will walk around and answer any questions, and we will reconvene in a little bit to go over some of the solutions, and also Philipp will give a more detailed introduction to some of the basic concepts in reinforcement learning. Hopefully that will be timed with around when you're starting the RL exercises. So for now, I'm going to stop talking, and please try out these exercises. Okay, thanks. So one clarification I want to make quickly is that when you call ray.init, it prints out a bunch of stuff, and in particular, it prints out a link to visit the web UI, so that link is not working. That's because we have a separate web UI that actually normally opens up a different Jupyter notebook, which is useful for debugging and stuff like that when you're running Ray locally, or you can do port forwarding. But because the notebook that you're in right now is being run on a separate EC2 instance that we started, and we didn't open the relevant port for the web UI, that link won't work, but it shouldn't be needed for any of these exercises. Actually, I also wanted to add that if you have questions, definitely raise your hand and we'll come around, but you can also just come up to the front and we can answer questions there, whatever's easier. Okay, that's all. Can you raise your hand if you've finished exercise 1? Okay. And can you raise your hand if you finished exercise 2? Okay. So let me quickly go over the solution for exercise 1. So we're going to start by just running starting Ray. And remember, I guess I already did that. There's this slow function, which basically sleeps for 1 second. And we want to be able to execute this in parallel. So we're going to start by adding the remote decorator. So now when we call slow function down here, we're calling it 4 times in a list. We can call it with .remote to invoke 4 tasks in a non-blocking way. So that will just submit the tasks immediately, and then return a list. This will be a list of futures or object IDs. And then we can block and wait for all the tasks to finish by calling ray.get to retrieve the results. And then if we time that, it will take 1 second because we did 4 1-second tasks in parallel, and that should finish the exercise. And then if you look at the timeline, so note this timeline will actually only work in Chrome. This is using it. Chrome has a built-in timeline tool. And if we zoom in to look at the actual tasks, so time goes from left to right, and each row corresponds to a different work or process. And you can see there are 4 tasks, 4 of these like slow function tasks executing in parallel. And if you zoom in even more, you can see the breakdown between how much time was spent executing the function versus serializing and storing the outputs. And so that's the timeline actually is really useful for answering questions like are things behaving as expected, or if they're too slow, what's going wrong, and where are things being scheduled. So in the multi-machine setting, you'll be able to see how things are scheduled across machines. So that's it for exercise 1. Yeah. So it's about 3 o'clock, and on the schedule there's a half-hour break from 3 to 3:30. So we'll reconvene at 3:30 and start off at 3:30 with the slides on reinforcement learning and the basic concepts of reinforcement learning, and then continue with essentially all of the exercises. So one thing I want to show you, if you've had a chance to take a look at the Pong RL exercise 5, you can see this is after, I think, either 30 or 40 or 50 iterations of training. It's actually starting to do something reasonable. It's not perfect, but it's at least better than the random initial policy. And so this is something you can try out yourself and play against the policy that you trained. This is RL exercise 5. So there's a short break now. We'll be around during the break, so if you have more questions, please come talk with us. Okay, thanks. All right, I think we're gonna get started again. So before Philipp goes over a bit about the basic concepts of reinforcement learning and what a Markov decision process is, I want to talk a little bit about when reinforcement learning is applicable and what kind of problems you can apply it to. So let's see. So here is one standard reinforcement learning benchmark. It's a simulation of a humanoid robot, and the challenge is to try to control the torques on its joints to get it to walk successfully. And so this is showing different iterations of a reinforcement learning training algorithm, in this case proximal policy optimization, on this problem. And you can see that after around 200 iterations, it's sort of able to stumble. After 500 iterations, it's actually able to run quite gracefully. The sort of key features about this problem that make it amenable to reinforcement learning are the fact that we have a simulator. So the ability to, so if you think about supervised learning, like classification problems, in order to, this is just continuing on to YouTube, I guess. So in order to, if you're thinking about, what kinds of problems, if you think about applying classification to a problem, you need to have training data. So you need to have data that you're trying to classify and then labels for that data. So in reinforcement learning, the ability to simulate something is analogous to data in supervised learning. Because in reinforcement learning, you're not trying to just generate predictions about some data point. You're trying to generate a sequence of actions. So what actions do I take in some environment? And in order to apply most reinforcement learning algorithms, you need some ability to simulate that environment. So that environment could be a physical, like a physics engine, like this robotics simulator. One example I'll show you now is with traffic. So let's see if, one second. So here I'm taking some slides from some other researchers at Berkeley, and there's actually a talk tomorrow on reinforcement learning for mixed autonomy traffic. Okay, so this is someone else's talk about using reinforcement learning, using Ray for simulating traffic. So here the problem statement is essentially, what if you have some fraction of the cars on the road are autonomous vehicles? So not all of them, but some of them. What can you do to sort of improve traffic flow and prevent traffic jams? And so here, this is sort of a naturally occurring kind of traffic jam that happens if you just let people drive in a circle. And you can do this experiment with real human drivers, and they end up, you have these waves of traffic. Here, this red car is the autonomous vehicle. It's sort of learning to set a steady pace in order to help control the traffic flow. And you can have more complicated. Oops. Wait a sec. I think the YouTube video is still playing on my laptop, so I need to stop that. So you can see, so you can have more complex traffic simulators that show traffic bottlenecks forming, at natural points of congestion, like this bottleneck right here. And so you can here's a naturally occurring traffic jam that occurs when you have a multi-lane, road narrowing, and so now I'll show you what you can do if you have some fraction of autonomous vehicles on the road. These are the red cars that are controlled with reinforcement learning. So they're able to control the flow of traffic a bit more in order to speed up traffic through the bottleneck. This is a great application of reinforcement learning precisely because you have the ability to simulate it. Now, of course, there's always a gap between your simulator and the real world, and so there's a lot of research into how do you take a policy that you learned in a simulation and transfer that to the real world. That's an issue with robotics, with traffic, and many other things. And part of the reason that reinforcement learning has mostly been, or is most successful with games like Go and Dota and Atari and things like that is in part because there's no gap between the simulator and the real world, because the simulator is the actual thing that you care about. But this is an area where people are starting to make a lot of progress on transferring from simulations to the real world. So some of these things are starting to become more possible. So the things that make a problem a good fit for reinforcement learning are being able to simulate it. That's sort of the big one. And other problems like having delayed rewards where you don't actually know you're taking a sequence of actions, and in the end you get some reward. Like maybe if you run a platform like Facebook, you are doing a lot of taking a lot of actions to interact with the people on your platform, and at the end of the day, maybe they leave your platform, and so that's some form of reward or negative reward, and you want to sort of attribute. You almost want to do causal inference, like understand which actions you took led to them ultimately leaving your platform, and these kinds of situations where are less of a good fit for standard supervised learning, but reinforcement learning techniques are more applicable. So those are some of the things I wanted to mention. So now Philipp is going to say a bit about the basic setup of reinforcement learning and how to what the sort of the primitive objects are in terms of the state space and the actions.
Okay, so the fundamental sort of data structure that RL is living in is this so-called MDP, a Markov decision process. And an MDP can be in a number of states. So in this case, it's a very simple so-called grid world MDP. And in this case, our states would be each of the fields. So this is a state 1, state 2, state 3, state 4, and so on. And then, so in this case, an agent would be in this first state. And it can then transition states. And that's done by doing actions. So it can do an action. It can either go left, then in that case it goes from this state to this state, or it can go up. In that case it goes from this state to this state. For the grid, there's also some walls, and they prevent certain actions from happening. So for example, if the agent was in this state, then it could only go left or right, but not up or down. So this is the MDP in the setting of a grid world example. But in other examples, how to think about this is in the following way. So for example, for the game of Go, your state would be the board and what stones are on the board already. And your actions would be where you can set a new stone. Then in the case of the walking robot that Robert showed earlier, the state would be the configuration of the robot. So what are the angles of all the joints? And the actions would be certain torques that you could do. So for example, if you're in this state, then maybe you can move your arm like down like that. That would be one action. And then in the case of the driving, the traffic, your states would be where your car is and where all the other cars are. And your actions would be what control you can do. And what control you can actually do depends on the level of simulation. If it's like autonomous driving, then your control would be, oh, you can like brake or steer or things like that. In a lot of simulators, you can also do higher level actions. Like maybe you can go left or right or things like that. Okay, so let's see how this plays out a bit more in the grid world example. So here I wrote down all the possible transitions between states. And then the goal of the reinforcement learning is to maximize what is called a reward. So in certain situations, you give the agent a reward, and the goal is to come up with a way to make the reward as big as possible. So for example, in the Go, the reward would be if you win the game, then you get a reward of 1, for example. And so the agent tries to win the game. In the robot example, the reward, for example, could be if you want to learn walking, then the reward could be your velocity forward. And so the agent would try to maximize the velocity forward. So in this case, there's a very simple reward. If you get the coin, then you get a reward of 1. If you hit the little enemy, then you get a reward of -1. And in all the other states, you get a reward of 0. Oh, yeah, in the Pong example, your reward would be the score. So how many balls, if you manage to get a ball past the other paddle, then you would get a positive reward for that. Okay, so now let's study this concept, what is called a rollout. So in order to get the best reward, you just try a lot of different things. So you remember that the goal of this is to get this policy, which is a mapping that tells you in each state what action should you do. So you start with some arbitrary policy, and then you just try it out and see how far it gets you and what sort of reward you get. So, and this is called a rollout. Trying out one such policy. So, for example, the agent starts in the state called C3. And then the action it takes at the beginning is left. Okay, we could say, oh, that's stupid because the reward is going to be here, but the agent doesn't know that at the beginning. So it will just go left, and then it will get a reward of 0. So now it's in the new state, B3. So what does it do next? Maybe the policy tells it to go right now, and then it gets 0 reward again. So it's back at where it was, C3. So now policy says go up, get reward of 0, go left, reward of 0, go up, get the reward of 0, go left, and then it gets the reward of 1. So now the episode terminates, and we record that we got a reward of 1 after rolling out this policy, and we also record how many time steps it took. And the goal is to improve that. So the reinforcement learning algorithm, and there's a wide variety of reinforcement learning algorithms. One that you could think about is, we just take like a random policy as a start, and then we just try to randomly change the policy and see if it does better or worse, and then we just keep it, the new one, if it does better, and we keep the old one if it does worse. So again, policy is a mapping from the state to which action it is. So in this case, it could, for example, be maybe it is like one probability to go into, there's a probability to go up, probability to go left, probability to go down, probability to go to the right. Okay, so let me make this a bit more concrete, how the learning happens. So again, the policy is a mapping from the state to the action. And what you want to maximize is this discounted reward. So you just sum up the rewards. You also want to get the reward as quickly as possible. So therefore, for the rewards that are further out, you apply a discount factor to them. So for example, if you get the reward in the next step, then you just get the reward. If you do it one step further, then you multiply it with some factor, say 0.9 or something like this. And then in the next step, you multiply it with 0.9 squared. So that means that the effect of the reward decays as the time goes on. So this is the objective that we want to maximize. This is one possible formulation. It's called a discounted formulation. There's also a bunch of other formulations, like, for example, you could also just not have this reward, Okay, so one very concrete setting where we can see this, and you will actually work on this and solve this problem yourself, is the card pole. So here the goal is to balance a stick on a card. And so the policy in this case is telling us, depending on where we are, do we want to go left or right, basically. And depending on what the angle of the stick is. So how does this look? So the state space in this case would be the position, the velocity of the card, the angle of the pole, and the angle velocity of the pole. And then the action space is would be, you can either do +1 in order to go to the right, or -1 to go to the left. And the reward would be for each time step, you get 1 if the position and angle of the card and the stick are within some bound. So for example, if the stick is still basically upright within some accuracy, and you get 0 if they're not. And you want to, so basically here you want to optimize how long you are balancing the pole. And this will be actually the, so you can define now a function from the state space to this set of actions, plus or minus 1. And then you can try to optimize and optimize the reward. This will be the first exercise. Okay, so now how this would work in pseudocode is you create this environment. The environment corresponds to this MDP. So that's basically telling you what are the states and what are the transitions between states. In this case, there's a predefined environment called card pole, which is this little simulator of the little card. And then you start off with an initial state by just resetting the environment. So that's the card being in the middle and the pole being upright. And then you do a loop. While you're not done, you evaluate this policy on the state, get a new action, and then you apply this action to the environment, and then you will end up in a new state. So we'll get the state, the reward in the new state, whether you're done, and some additional information. And this is a pseudocode of how you do these rollouts. And now you try these rollouts for a lot of different policies, and you just take the policy that did the best. That's basically going to be the first exercise. Okay. Yeah.
So now we'd like to go back to the set of all the exercises that we're working on, and continue from there. If you haven't had a chance to look at the RL exercises yet, please take a look at those and get started with those. Then, in particular, I want everyone to have a chance to do the Pong exercise, because that one synthesizes a lot of the concepts in other exercises and in sort of a fun example. Yeah, let's continue. And if you have questions, please come up here to talk with us, or raise your hand and we'll find you. Yes.
You say the tutorial or slides are online?
Yes. So if you go to like GitHub, so Ray itself is on GitHub. If you go to the like Ray project GitHub organization, there's a tutorial repository, which essentially has everything that we're going over today. Yes. Any other questions right now?
Can you upload the PowerPoint?
Yeah, I think, yeah, I can do that. Great. One other thing I want to add is that we actually created a lot more material than we have time to go through. So if you don't have a chance to go through everything, that's sort of, I think most people probably will not have time to go through everything, so that's expected. The content will be available on GitHub. But so at this point, you should probably just pick and choose which exercises look interesting to you. But definitely don't feel bad if you don't get through everything, because we tried to generate more content than what we'd have time for. That's all.